Hi, in this video, we'll be building a multivariate time series model using recurrent neural network. Recurrent neural network is a type of deep learning neural network architecture used specifically for sequence modeling. So let's get started. So what I'm going to do is I'm going to import the necessary libraries to import the data and visualize the data. I'm having pandas to import the data set, matplotlib to visualize the data. I have model selection to split the data into train and test. Then I have like a time series generator, which is for data preparation of time series model. So it's in the Keras pre-processing package, and I am importing time series generator. From the sklearn pre-processing package, I am importing standard scalar and min-max scalar. I'll be using only one of it, but I will tell you like why I'm using the necessary scalar. And then I'm importing TensorFlow to define our LSTM architecture. So that's what I'm importing. So once I have this, I'm going to download my data set. My data set is in the UCI machine learning library open data set. So I'm going to use the energy data from that particular UCI library, and I'm assigning it to a data frame. So once I get download the data and run it, you can basically see there are like close to 19,735 rows and 29 columns. So you can see over here on the top, you have all the date, appliance, light, the energy usage for the appliances, the energy usage for the light, and then there are a lot of T1 RH1 and T2 RH2. I will tell what are these columns. So the date, if you see, we have data collected every 10 minutes. So basically these are like smart meters that are fitted into an house, and the data is collected every 10 minutes, which tells us the appliance energy usage and the lights energy usage. And there are a lot of other parameters like temperature. All this T1 is temperature and RH1 is humidity. So I have defined the columns below. I have taken it from UCI and pasted here. So the appliance is basically nothing but an energy usage in watts, and the lights is energy usage of light in watts. So when I say appliances, these are like heavy appliances like your washing machine or even like heater, AC and all, right? Lights are general lighting that you use in the house. The date is the time, which is every 10 minutes the data is captured. And I have like temperature and humidity for each and every room in the house. So I have the kitchen area temperature, kitchen area humidity. I have the living room temperature, living room humidity. Similarly, for each and every room in the house, the temperature and humidity is captured. Apart from that, there are variables that capture outside temperature, like TO stands for temperature outside, and pressure stands for like outside pressure, humidity outside, wind speed, visibility. So all this inside the house information temperature, outside the weather information is all captured. So there are 29 variables, but what I'm going to do is I'm just going to use subset of the variable for our purpose, just to demo the multivariate time series. But let's see like what is the data type of all these columns. Most of these columns are in float. That's what we want. The date is in object, but in order for us to visualize and make some time series slicing and dicing, we want date to be in the date time format, right? And the appliances and light is in the integer format. That is, appliance is going to be our target column that we are going to use. So what first thing I'm doing is I'm converting the date column into date time. So basically the date column, if you saw on the top, was object. So I am reading it, I'm doing a pandas.to date time, and I'm telling infer the date format. If you know the date format, if you can also give it, but also you can allow pandas to automatically infer the date format. So once I have it, if I go back and basically run this again, you can see the date time is now an date object. Not, if you see the date times, they're not an object anymore. It's like a date time data type. Right now, what I'm going to do is I'm going to quickly generate plots of a specific columns. I'm not going to use all the columns. So I am setting the date as index, and then picking the appliance column, lights column, output temperature, humidity, and then the visibility. Right, so these are the columns I am picking. I'm creating plot of each and every variable. So if you see here, you will get like multiple plots, and this is how it looks like. So this is how the appliance usages. You can see some spike on the beginning of the year, and then it kind of like kind of stable, but there are spikes intermediate, right? Now if you see, the data is from February 2016 to May 2016, so you can assume like the initial Feb month, it's going to be more like winter, or it's not going to be hot as the further month. So during winter the usage is higher, and you can see that even the temperature out, the temperature is pretty low during the initial month, and you can see a behavior that the appliance usage spikes up. And similarly on the lights usage as well, the lights usage are higher during the winter month because it's going to be darker earlier, and during the summer it's less, right? So basically that is the pattern. And similarly you can see like visibility and humidity, how it correlates. So now what I'm going to do is I'm going to create another data frame. I'm going to use the output temperature, visibility, and the humidity and the appliance as my new data frame. I just created with a subset of column which I'm going to use for my model. So this df input will have this four columns, right? I'm going to use these four columns are going to be my input in the multivariate time series model. Let me quickly describe the column, and just to see like how the distribution of data looks like. Now if you see in the appliance, the 50%, the median is around like 60, the mean is around 97, but the maximum is at 1080, right? So there are extreme values. And similarly the temperature is basically the mean is around 7, and there are some max temperature. So yes, the data is kind of having some outliers. So let's quickly see. Let's take just like some greater than 500 appliance usage, and see like how much outliers we have. So we can see around 288 outliers are there. I'm just taken 4 or 500, but you can take 100 also, because 100 is the maximum 75% value on the top. So you can take 100 also, but there are 288 columns. So in order for me to account the outlier, what I'm going to do is when I am scaling it, I don't want to use the standard scaler, because standard scaler will not account to outlier. I will shift the mean and standard deviation. So I'm using a min max scaler here. The reason I am scaling the data is before feeding into a neural network model, I want the gradients to converge faster. So that's why I'm scaling, so that it has a standard mean and standard deviation for the gradients to converge faster. If you don't scale it, it may take a lot of time to converge. You can try with that also, but it's a standard best practice to scale the data. And I'm going to use a min max scaler over here. So I'm setting the min-max scaler. I'm passing this input data frame. I'm calling the scalar.fit transform. I am passing the input data frame, and I'm getting the scale data. So with this, what the scale data is going to do is it's going to basically scale the data so that it's between like 0 and 1. Now, what you can do is when you're having multiple data frame, you can just scale the data for the training data frame, and then you can use the scaled value for your test data frame, assuming that the distribution does not vary much. In this case, I have just used a single scalar, but when you are developing in real term, depending on your data distribution, you may want to take a call whether you want to kind of scale it based on the trained value, or you want to do like based on the test value if the test is completely different. But the best practice is you use the training data frame, you define your scalar on that, and use the parameters from the training data frame into your test and other validation data frames, right? But in this case, I have that just done for every data frame. Okay, now what I'm doing is from this data, I have defined basically the first four columns as my features. So I am passing all these four columns, even the appliance value. The appliance is going to be my input as well as my target, and then the temperature, the humidity, and the visibility, I am giving that into the features column. And the target column, I am only taking the zero index, that is the appliance. So basically once I run this, what is going to happen, all these four columns are going to be my input. These are going to be my multivariate data to the input of LSTM model, and the target column is going to have only the appliance usage value over here. So basically I'm taking the prior appliance usage and along with the temperature and everything, and I am predicting a future value what it can be. That's what here it is. So the appliance is that as part of input and output, but the output will be a future value of appliance, and the appliance during the training process will be the current value. I will explain what I mean by that. So here in the time series generator, I'm going to use to prepare the data, I am passing my feature value, which is all the four columns, and target value, which is the appliance column over here. I am telling my length is equal to 2. So my window length, I am going to take a two time periods of data. So in this case, it's 10 minutes data. So basically, I'm going to take 20 minutes of data, and I am going to predict the next one, right? The 30th minute, what will be the value? It is for sample. So I'm just taking the simultaneous generator. I'm getting the first batch. I've given batch size as 1, but in real world, you want to give a larger batch size, and I'm just printing the output. So what you can see is it has taken the first training instance on top, the 0.46 and all. It has taken the second training instance, so it has taken two time periods of data because length equal to 2, and it's predicting the appliance value of the third. The output is the third. So these two are input and this is the output, right? So this is how we are going to feed the training data, right? But I'm going to feed for more time steps. I will come to that to just to show the output. This is how your input and output will look like. Your input will be a list of values of your input multivariate data, and the output will be your appliance data. Now, very first thing before using the time series generator in with the real time window, I'm going to split the data here. I'm going to use like take the futures and target. I'm going to use a train test split, and then I'm going to use the test size as 20%. So basically 80% will be training and test size will be 20%, and I'm telling shuffle equal to false. This is very important because it's a time series data. The order is very important. If you don't give, it will become shuffle equal to true, so it will randomly shuffle and split the data, so you're losing the order. When you define a LSTM model, you don't pass time at all, you just pass the features. But when you're defining a Facebook profit model, time is an input parameter, right? But so you need to make sure that when you are passing the data is in the same order, right? So what I'm going to do is I'm going to split the data, test and train, and you can see my train shape and test shape over here. Train has around 15,788 instances. There are 4 features, and then test has around 13 3,947 instances and 4 features. Right now, I will define my time series generator, the actual time series generator that I am going to feed into the model. So what I'm doing, I'm defining the window length. In the previous one, I gave window length to 2. That is just for sample. I'm here defining the window length as 720. So what the 720 means is I have data every 10 minutes. So for 1 hour, I have 6 data points. 24 hours, I have 24 into 6 data points. So on a day with 10 minutes interval, I have 144 data points. I am taking 5 days of data. So that's why it's 720, 144 into 5. So each day I have 144 training instance. I am taking 5 days of data, and using this 5 days of data, I am going to predict the next observation. And that's why I've given window length as 720. I have given batch size as 34. I don't want to train one record by one record because I need my training to be faster. I am defining a batch size of 32 so that in each training instance, I am passing 32 batch size of data. And then the number of features is 4. That's our input feature size, that is 4. And I'm creating a train generator and test generator. In the train generator, I am passing the X of train and Y of train, which is nothing but the 80% of the data. I am telling my length is 720 over here, which is take 5 days of data and predict the next instance. The sampling rate is 1 and the batch size is 32. And similarly, I am defining the test generator based on X test and Y test data frame. So quickly, let me predict the train generator. And you can see basically it will contain 32 because the batch size is 32. It will contain 32 observations, each of length 720, each having 720 observations, and each observation having 4 features. And then finally you can see there will be the target column. There will be 32 target columns because there are it's a batch size of 32, right? So that's how it looks like. Now we will go and define our model architecture. So what I'm going to do is I'm going to define an LSTM model. I have multiple layers here. Here what I'm doing is I'm creating a sequential model instance, and then I'm telling my LSTM layer basically number of units is 128. My input shape is my window's length. Window length is 720 on the top, and comma 4. So basically I have 720 instance with 4 features. That's my input shape. and then I'm telling return sequence equal to false. Return sequence equal to true. And why you give true is basically now you need a hidden state for each of my input data. If I give it false, it will only return one hidden state for all the input sequences. But here it's a time series data. I want to take each and every observation into account, so I need to have hidden state for each and every observation, and that's what the return sequence does. Right, I am using a leaky relu activation function, and then similarly I have one more layer with another 128 LSTM layer, and again a leaky relu. I have a dropout just to make sure it does not overfit, and then again I have an LSTM layer with 64, and here I am telling return sequence is false. So in this case I will return only one. It will return only one hidden state. I can still return true, and I can have a dense layer. I can flatten it. I can have a dense layer, but here I'm just creating false, and I am creating a final layer of one, which will basically give me the final prediction of what is the appliance usage in the next hour based on the input data. So this is my model architecture. Let me quickly run my model.summary, and basically you can see over here how this particular model looks like. Okay, this model has around 250,000 parameters, right? Then I am defining my model. So what I'm telling early stopping. I don't want to run forever, so I am giving like 50 epochs here, but I'm also giving a early stopping, that is telling if the validation loss is not improving at least two iterations, then basically stop the training, right? That's the early stopping Keras callback I have. I am compiling the model using a mean square error, and my optimizer is Adam, and I am giving the metrics to monitor as mean absolute error, right? That's what I have given over here. And I am calling model.fit generator. You can also give model.fit with this, but I'm giving model.fit generator. I'm passing the training data frame, and then I'm telling my epochs is 50, but it will not run for 50 epochs. If the model sees it's not improving, it will stop based on the early stopping callback. I'm telling shuffle equal to false. We must not shuffle the data by default, right? So because the time series data, the order is pretty important. I'm telling shuffle false, and then I'm telling my validation data as test generator. It's typically good to have one more slice of data for testing the data, but here I'm just using the validation data for both the purpose. It is good for this video, but in real world you may want to have train data, validation data, and test data separately, right? So this is the model architecture. Let me quickly run this. It's going to take some time to train. So what I'm going to do is I'm going to wait for it to complete and then come back. But let's quickly see one epoch, so you can see basically it's training. And make sure you have GPU on. Even without GPU this will work. Only thing is it will take some time. I have set GPU in the collab, so you can see basically the loss is decreasing, the mean absolute error is there, and let the training complete, and then I will come back and continue with the video. So model is trained now. It took 10 epochs to train. Because of early stopping, it stopped. And basically you can see over here like the mean absolute error validation is 0.284, and the loss is 0.040. Basically the training mean absolute error is 0.03. So this is the model we have got. Let's see how well this model performs with the test data that we created. So let's evaluate this particular model with the test data that we have and see like how it performs. So basically you can see the mean absolute error is 0.028. What I'm going to do is I'm going to go and predict the value, and I'm going to compare it against the actual value, how well the model did. Okay, so I'm calling the model.predict generator, and I'm passing the test generator. I'm getting all the predictions. Now, once I pass this, if you see basically our test data frame had some 3,984 records or something like 3,947 records, right? The test generator. So once it's done, let's see the shape now. So it has only 3,227 rather not 3,947. The reason is you can see there's a difference of 720, and 720 was our time step. So when we are passing the data to the prediction, it's going to take the first 720 columns to predict the next, and after that it's going to keep on sliding next to all the values. So you will always have numbers less than the window's length. The window length is 720 for us, right? So let me quickly print the prediction. And if you see, this is the prediction. If you actually see, this is the appliance output. But if you see our actual data set, the appliance output was like 60, 70, 100 whole number, and this is actually scaled prediction. Now we need to do a inverse of the scaling and get back to the original prediction and compare our model how it has performed, right? So let me quickly print the y test. And if you see the y test, this is what it looks like, the 0.33, and this is what you can see, right? Basically y test is also a scaled value. Now what I'm going to do is I'm going to take from the x text, right? So these are all the different data that we had, right? I'm going to take the all the data from first column till the end, and from the window's length. So window length is like 720. So I'm going to ignore the first 720. The reason is our prediction value does not have the first 720. It has only 3247 records or something like that, 3227 against like 3947 records that the actual test data had. So I'm just taking the ignoring the first 720 and taking all the value. I am going to create like a concatenation of the data frame. I'm going to take all this from the X text, and then I'm going to take the predictions from what we got, and I'm going to concatenate and build one final pandas data frame. So basically, I will have like a data frame which will have the predicted value and which will have all the values from the X text, right? Rather than having the actual label, I have the predicted label. That's the change I have made. And I am going to take the scalar that I created on the top, and I'm going to run an inverse transform, and I'm going to pass this predicted value. So if you see this particular df underscore pred, right? Df underscore pred, it will have these four values over here. Right now, these are all scaled values. I need the original values, and for that I did a scaling on the top. I use a min max scaler. Now I need to do a inverse transform. That's what I'm doing over here. So once I run this inverse transform, and now let me print the reverse transform, you can see the values into the original format, right? So now I have this data frame over here. Basically I have all the columns, and I have the this is a predicted value. Right now I need to take this predicted value and compare how close it is to the actual value, right? So what I'm doing in the df input data frame that we created on the top is the actual data frame. So the first 80% is the training data, the last 20% is what we use for prediction, and that is what it is over here. So basically what I'm doing is I'm taking from the df underscore input, I am getting the prediction shape. So the prediction shape is what it is actually 3247 or something like 3227, right? And I am getting the last 3227 rows. This last 3227 rows is basically our prediction frame that we are using, and that's what I'm doing over here. So basically it's going to take the last, when I say minus into minus one, basically it's going to take from the bottom to top. When I don't give minus, it's going to just take top to bottom, whatever size we have given. But here I am doing minus one, so it's going to go from bottom, right? So once I have this df final data frame, if I do an kind of count, you can see it as 3227, which matches our prediction frame on the top, right? Now what I'm going to do is I am going to create one more column in the df final, which is the appliance usage predicted value. And in the reverse transformation that I did on the top, I am just going to pick the first column over here. That is the predicted appliance value. So that's what I'm doing over here. I am creating this, taking this predicted appliance value, I am attaching to the df final data frame, which is the app rated. Now if you see the output over here, I will basically have this is how it is. So this is the appliance actual value 90, the predicted value is 83, 120, the predicted value is 112, 390, the predicted value is 138, 240, 367. So basically this is how it looks like. You can see somewhere the peak like from 120 to 390 when it goes, it is not like drastically predicted. So the peaks look like as not predicted properly. So that's why maybe we need to do some more feature engineering and feed it to our LSTM model. Maybe the features that are there like temperature and humidity are not completely represented the usage. Maybe that day was a holiday, or maybe you need to go at the hour level and see if there is any peak usage spike during the hour. There are a lot of factors that we can try out, right? But we the numbers look somewhere close, right? 90, 122, 100, 108. There are a few differences. So now let's see like how the plot looks like, right? I'm taking the appliance value and the predicted value, and this is how a plot looks like. And you can see basically the blue one is the actual value, the orange one is the predicted value, and in a lot of cases the orange one has come pretty close to the actual value. The peaks and all, if you see basically the it's kind of the orange value has clipped off. It didn't recognize the peak. The reason is if you also see the data has some trends over the time, right? The appliance usage has been increasing. Maybe it's not able to capture that particular trend. Either we need to detrend the data and pass it, or we need to build features that can complement this trend data, right? But we got a pretty good decent model which is somewhat able to recognize the shift in data and the appliance usage. So that's about it in this video. Thank you very much.